Hi everybody, we're here at EST-STAR, the European Center for Theoretical Physics in Trento, Italy. We're together with a lot of students. We are 3 students, one of the professors. And the school is about QCD, quantum chromodynamics, about everything like in the proton. And we were discussing a bit about the Higgs and mass in general. And the point is, there is this common misconception. People think that the Higgs is responsible for generating the mass of everything we see.
It's not.
It's not. It's partial, really tiny amount. And we thought maybe we can share this with you. So we made a little video trying to explain how this happens actually. We did it in few parts. So first, Mike will explain us zooming down several levels of magnitudes and see what happens. Where is the mass? Right? Next, Abe, he will talk about the electromagnetic interaction. At some point we stop at the atom. Let's see what happens there. Next, I will continue. We go further down to the proton. What happens there? And in the end, Josh will tell us where is the mass located. We can tell it now. It's the gluons. So what are gluons? Keep on watching.
Okay, so we've been talking about where matter comes from. And I think, and specifically where the mass of the matter that we can see comes from. And in that vein, I thought we should look at what matter is on a series of scales and talk about what interactions in physics becomes important with each scale. So if we start with just a regular chunk of matter, let's call this 1 meter wide. And we can ask, where is this matter coming from? Where's the mass of this matter coming from? Well, we can start by looking at the atoms inside of this matter. So if we zoom far down into this piece of matter, say to the scale of 10 to the minus 10 meters, the structure that emerges is this electron orbital and a nucleus. Now, if we look at the electron and the nucleus separately, we find that almost all of the mass lies inside of this nucleus. So we could stop here and say, well, we have mass because nucleuses have mass, but that's not true. I mean, that's true, but that's not where the mass comes from. So if we zoom in another level, to the level of the nucleus, now we've gone down in scale 10 to the minus 14 meters. And at this point, we start seeing these protons and neutrons emerge as discrete structure. And we see that they're bound together with this residual nuclear force carried by pions. And so if we ask ourselves, okay, where's the mass in this picture? Is it in this field of pions or is it in the individual nucleons? But it's in the nucleons. And so we now know that, okay, our mass is focused in a small area, 10 to the minus 14th meters per atom. Well, that's not the end of the story either. If we zoom in on one of these nucleons, we come into the scale of, we begin to enter the scale of quantum chromodynamics. And so, at this scale, we're at about 10 to the minus 15 meters. And we see even more structure emerge. We see these quarks bound by gluons in a very tight configuration. And if we look at the quarks here, and we ask ourselves, where's the mass living? The quarks actually don't have most of the mass. In fact, the mass of our nucleons is somewhere else. So we have to look a little bit deeper. Let's just pick any spot inside of a proton. Let's look here. You zoom in again, and now we're on scales of less than 10 to the minus 15 meters. And at this point, you just see the sea of quarks and gluons. And if we use Einstein's mass-energy relationship, and we look at the mass held by the energy and momentum of these gluons, we find that most of our mass actually comes from these fields of gluons. So our body is actually made of glue. And if we look at where this mass is stored relatively in location, we find that the vast majority of our body is just this empty space. So between an electron and a nucleus, there's just space, empty space. Between these protons and neutrons, there's empty space. And when we finally get down and look at what this empty space is, it becomes this massive quantum chromodynamical vacuum, just roiling with gluons. And the mass, our mass originates there.
Okay, so let's see how an atom works. In this atom, you know that there is a nucleus in the center, and it's held together, holds together an electron around it. The entire atom is almost empty. It's full of complete vacuum. The size of the nucleus with respect to what is shown as an atom is like having one p in a cathedral. So if the atom is the cathedral, the nucleus is 1p. That's the size. So it's basically completely empty. The electron is held together inside by something called a photon. Photon is the charge carrier in the electromagnetic force. Photon itself is chargeless. It requires two charged particles. If it is one is positive and the other is negative, then the exchange photon gives you an attractive force. If the two charges are like, meaning they're all the same, either positive or negative, then this force will be repulsive. But the photon itself is chargeless. So you can never have a photon interacting with each other. This kind of a interaction will never occur. What is the distance dependence of this electric force? If you take two charges, unlike charges, they will attract. As you pull them apart, the force between them will keep on decreasing as a function of distance. If they bring it together, they will increase, which is also is going to be different with anything else that you see inside the proton. And the continuous exchange of this photon between the electron and the nucleus makes it feel that there is this electron, there is the nucleus, and then there is a exchange of this photon. It pulls the electron in, does it again, tries to. So eventually you have a picture of an electron going around in a fixed orbit and continuously exchanging photons with it. It looks like a spokes wheel of a bicycle.
So let's take a closer look at the proton. So the proton consists of 3 quarks and some bunch of gluons. That's the basic idea. So the main idea is a bit the same, like the electromagnetic force. We have a gluon, which is a force carrier, which keeps the quarks together. However, there are some big differences. For one, in the electromagnetic case, we had the wheel, right? The photon being exchanged to the nucleus all the time, so there is some kind of center which the electron is orbiting around. In this case, this is not the case. We have the proton with 3 quarks, and then we have the 3 quarks held together by gluons. So there is no center. That's one important difference. Secondly, the way the force acts is totally different. In the electromagnetic case, like with magnets, the closer you go, the stronger the force will be, right? You know this from magnets. If they're really close, the force is strong, sometimes difficult to separate. For QCD, which is the strong force of gluons, this is totally the inverse. the closer you go, the weaker the force. So two magnets would be really easy to separate, but more and more difficult the farther away you go. You can see this as like a rubber band, right? The more you stretch it, the more it tends inward. So the more you stretch it, the stronger the force becomes tending it back in. This is a bit how quarks will act. Imagine we have two quarks at some point, and they are continuously interacting, sending out gluons to each other, right? So if you try to separate the quarks by moving one of them more apart, the force will become so much more stronger that we have really a bunch of gluons inside it. The gluon field becomes really strong. At some point, what would happen if you have a rubber band and you stretch it too far? It will break, right? That's the same what happens here. At some point, the force in between the gluon force field will break. In this case, it would mean two new quarks appear. One of the gluons will become a set of quarks, so that in the end, what happens? We have two sets of quarks. So you can see here, the force is so strong, so two new quarks appear, and they stick together to the original quarks, and we have two sets of quarks. So the main idea, it's never possible to separate a quark. Always when you try to separate it, new quarks will be created. How does this work? How does this come? This is because in the electromagnetic case, we have two charges, plus or minus. Now, in the quantum chromodynamics case, we have much more. We have colors, not real colors, but we like to call them colors. They are red, green, and blue. And then they're inversed, which are anti-red, anti-green, and anti-blue. I put a bar over it to say that it's anti. Okay, so why are they called colors? Because quarks will always appear in color neutral, like we call it, combinations. Color neutral means white. What happens if you mix red, green, and blue? You get white. It means that three quarks can come together, form one object, and be colorless, like a proton. In the proton, we have red, green, and blue, a colorless object. You can also have two quarks together, red and anti-red. If you mix red and its inverse, you get white again. So that's why we have two quarks here. They are colorless, color-neutral objects. That's the main idea. Now, to change the colors of quarks, we have gluons, because they will interact, like always. In the electromagnetic case, the same. The force carrier interacts with charged objects. Now it's called color charge. So let's take a red quark and a green quark. Now, what the gluon does in this case, it takes away the green color and it brings in the red color. So the anti-red doesn't matter actually. Let's say the anti-blue color. So at some point, I'm screwing up a bit with the colors, doesn't really matter. Okay, so the point is the gluon itself is colored. This is really important because the gluon itself will interact with other gluons. Because the gluon is colored, the force carrier couples to colored objects, so the gluon itself interacts with other gluons. So it means that in this picture, three quarks with gluons, the gluons itself, they can interact with each other. And we have lots of gluons. And of course they can separate again into quarks, so we have also lots of quarks. So in the end, the most important difference between the atom electromagnetic case and the quantum chromodynamic color proton case, the atom is almost empty, the proton is full of quarks, and more especially full of gluons.
Alright, with my friend Frederick here, we're going to try to figure out where his mass is located. So, what is your mass?
76.
Alright, kilograms. The mass of our Frederick, 76 kilograms. Alright, so as we've seen going through here, well, where can this mass be stored? Well, here's his skin and bones and everything. Here in the atom, who's our child, we have our electron. Well, maybe the mass is stored in the electron. Well, for the atom, the electron is only about 1 part in 4,000 of the mass. So for the mass of that's held by the electrons, all the trillions of electrons in Frederick here, we take our 76 kilograms of Frederick. That's only 1 part in 4,000 for each of the atoms. So that's only about 20 grams. So all of Frederick's electrons
It's like a chalk.
piece of chalk. Exactly. So, it's not the electron, well, the nucleus. Well, we know the nucleus isn't just a constituent piece. It's not a basic piece of the universe. We have our protons and neutrons. But we know there's things even smaller than that, so are quarks. Well, so what's the mass of Frederick's quarks? Well, his 76 kilograms, that's about 1 part in roughly 2,000. So it's more like 40 grams, but there are 3 quarks. So this comes out to times 3. So this is maybe 120 grams worth of quarks.
6 chalks.
6 pieces of chalk. Nice. So it's not the quarks. So is it the gluons? So try to figure out how much of the mass of how much mass of Frederick's mass is carried by the gluon.
Almost everything, right?
No,
The gluon.
nothing. The mass of the gluon is 0.
Oh yeah.
So the gluon's not part of the mass.
But we saw the glue that binds us, right? The gluons take all the mass.
Right, but it's not the gluon's mass itself. It's the gluon's kinetic energy. It's all of this energy in these fields of the gluons being exchanged between quarks and other gluons. So the way that we get that mass through our good old Einstein, right? We just have the energy from those quarks, and that gives us the mass of Frederick. So it's not the electrons and the quarks, and it's not the gluons themselves, but it's the kinetic energy and the exchanges of the QCD field giving this mass.
So almost all my mass is just the movement of the gluons inside me. Take that, Higgs.
He's very kinetic.
Yeah.
Alright, so there's a small correction to this part of the calculation. I assumed the mass of the quark was equal to the mass of the electron, but the mass of the quark should actually be about 8 times the mass of the electron. So if we take our result here times 8, this should be about 960, or you're about 1 kilogram, or Frederick is about 1 kilogram of the constituent mass from the quarks.
Okay, so to conclude, like we said, the mass, like almost all mass of our body, of everything, is in the gluons. So what did we do? First we looked at the scales, going down to several sizes. At the atom, it's the realm of the electromagnetic interaction with the photons, almost vacuum. We go more down, we go to the proton, the realm of the strong interaction, full of gluons. In the end, it's the gluons, all the gluons, which will carry all our mass. Not the gluons themselves, but their energy, right? Because themselves, they are massless. So here we did the calculation. In the end of my 76 kilogram, 2 gram is the electrons, almost 1 kilogram is the quarks, so the remaining 75 kilogram is gluons. These 2 parts, electron quarks, would be Higgs interaction, so we can say that the Higgs is responsible for 1.25% of my mass. Saying the Higgs gives mass is an overstatement, I would say. Alright.
Hi guys, I hope you liked the vid. There are new science vids coming up, so feel free to subscribe if you like it. Also feel free to make any suggestions you have. I will see what I can follow and whatnot. A little update for those who are interested. The neutrinos don't go faster than light, as CERN a few days ago admitted. it was a mistake somewhere in the machinery. I posted a link in the description so you can see, read the article yourself.